Howdy, folks. Welcome to the our department's SLOS seminar, where it's the second week in a row of atmospheric science. You're welcome.
I don't
know. It is my pleasure to welcome, and I'm going to do my best with your beautiful name, Akintomide Akinsanola. Is that okay? All right. Thank you very much for visiting us.
Thank you for having me.
He comes to us. I was looking at the list of all the places he's been, and thinking that he beats me out in terms of the directionality of all the different places he's been. His roadmap to academia is quite distant. So he got a bachelor's and a master's in meteorology from the Federal University of Technology in Nigeria. Then he got his PhD in climate science from City University of Hong Kong. So I think that already beats all of my travels right there. And then he did a couple postdocs, the first one at University of Georgia in Athens, Georgia, and the second at Argonne National Lab. And then, as of this fall, he's begun as an assistant professor at the Department of Earth and Environmental Sciences down at the University of Illinois, Chicago, where he still holds a joint appointment with Argonne National Lab. So, welcome to the Chicago area. It's great to have another atmospheric scientist around. And today he's going to talk to us about some of the modeling work he's done to look at precipitation. So, thanks for joining us.
Thanks. And thank you everybody for attending my talk. So today I'll be talking on seasonal extreme precipitation over the US in Earth system model. And we'll explore the potential added value of high resolution and super-parameterization. So my talk is, I will briefly give a motivation for the research. We'll look at the seasonal extreme precipitation over the United States in the coupled model intercomparison project, version 6, the recent one. Both the evaluation of the model and also we explore the projected changes. The second part of the talk will look at the potential improvement from high resolution going up to about 2.5, 0.25, and also the superparameterization. So for superparameterization here, the idea is to have like an high resolution embedded cloud resolving model at about 1 to 2 kilometer scale on the original configuration of the model, which is about 100 kilometers, and the conclusion. So when we look at precipitation characteristics, both the mean, intensity, frequency, amount, these can influence the availability of fresh water as well as occurrence of drought and flooding, and has significant impact on the ecosystem of the country and the overall economy. So, and the US in particular, which this study is focused on, has experience of series of events of extreme, which has resulted into thousands of deaths and billions of dollars in damages. So, given the importance of precipitation in our daily life, so realistic representation, or accurate representation of precipitation in Earth system model is essentially crucial. And this representation, we are talking about looking at them across a wide range of spatio-temporal timescale. Unfortunately, when you look at the generation of the model we have, especially those that participated in the coupled model project, the SEMI-3 and the SEMI-5, there has been little improvement in the ability to represent precipitation, particularly when you look at the frequency and intensity of the daily precipitation. So the two previous generation, the common problem among them is they tend to simulate precipitation that is too frequent and also too weak when you compare with observation. And because of these limitations, so how extreme precipitation is going to change globally and regionally, particularly over the US, is still fraught with a high level of uncertainty. Partly based on what I've told you, that the GCM failed to accurately simulate the frequency and the intensity of regional precipitation events. So in recent time, there has been the release of the SEMI-6, which is the latest version. So the SEMI-6 model has included a lot of updates in terms of the physical processes, horizontal and vertical resolution, and also transitioning to a new emission scenario called the shear socioeconomic pathway. In the previous version, it has always been the RCP scenarios. So, based on these updates, it is thus crucial to evaluate the capability of the model that participated in the CMCs in accurately representing the present-day extreme precipitation over the U.S. And we're looking at it in terms of their spatial and temporal variation. Also, it is essential to see whatever improvement we see in the present day, if that translates to improvement in the projected changes. So the last aspect is to explore the potential added value of high resolution or super-parameterized configurations.
I think if you move your mouse a little bit, that top thing will go away.
Okay. Yeah, perfect, thank you. So the two critical questions this talk will be answering is how well do CME6 model? Again, CME6 is coupled model intercomparison project, the version 6, including the E3SM. E3SM is a DOE baby, energy exascale system model, which we are going to look at in detail. Represent extreme precipitation characteristics and their projected changes. So this is an extract of 2 papers published in Environmental Research Letter. The last aspect is, do high resolution and the super-parameterized configuration provide more realistic representation of daily precipitation characteristics? We also published this in GRL this year, and the details of the papers are here. So for extremes used here, we are looking at the expert team on climate change detection indices, about 9 of them, ranging from the CDD, which is the consecutive dry days, looking at days when you have less than 1 millimeter per day of precipitation. You have consecutive wet days, opposite of these, greater than 1 millimeter per day. So these are more heavy rainfall events, total rainfall of greater than 10 millimeter and 20 millimeter. This is the total precipitation. This is the more extreme part when you're looking at the 99% precipitation. You're looking at maximum consecutive dry day of precipitation here and daily intensity. So, and also to evaluate, the practice is to compare the model with observational data sets, graded observation. So here we're using the Climate Prediction Center data set, CPC, the Global Precipitation Climatology Project data set, the Tropical Rainfall Measuring Mission, and the IMAG. Why we're using multiple observations is my study and also previous studies have shown that there are also high level of uncertainty among the graded precipitation products, such that sometimes the model are more associated with some observation than the others. So the model we considered here, so all the models here listed here were used in the evaluation. The one that were used for the projection were the one starred in red. Generally, the model that comes in different horizontal resolutions. So in a way for comparison, the common practice, the best practice is to regrade all of them to the lowest model in the data set. For the projected changes, we compare the future time slice of 2061 to the end of 21st century to the historical time slice of this period. And in a way to assess how robust our projection is, we assess if the change is statistically significant at 95 using t-test. And another additional statistics we look at is does 70% of the assembled members agree on the sign of change in the assemblement? So if 70% of all the listed model here agrees on a particular sign, then we can assume that the projection is robust. So we focus mainly on the summer and the winter period. So for the evaluation, I present the result of the frequency and amount distribution, seasonal frequency and amount distribution for winter DJF and for summer. So here, so you have the multimodal assembly of the 76 model listed. The shading is their confidence interval. So we isolated E3SM, which is the DOE energy exascale system model here. And the two observations which we are using is the CPC, which is the black solid line, and the faint or the great line is the tree. So generally, when you look at the frequency and amount distribution in both seasons, you can see TRIM data set has much lower frequency of rain even than the CPC observation in both seasons. And the semi-6 model, alongside the E3SM energy exascale model, has a much higher frequency of rain than the two observations, and is nearly twice as frequent as that of TRIM. Similar bias is also evident for the amount distribution. So when you look at the amount distribution in the winter and also in the summer, you can see the peak of the precipitation rate in both observations is higher than the observations. And this is particularly obvious in the winter compared to the summer. So you can see both the model, both the assemble mean of the semi-6 and the E3SM grossly overestimate the amount distribution of precipitation. Now, aside from looking at the area average distribution, so we look at the spatial distribution of the mean precipitation. So this is from the two observations, CPC and TRIM, for winter and the summer. This is the multimodal assemble mean of the semi-6, and this is the E3SM. So when you look at the spatial distribution, climatologically you have high precipitation in the tip over the northwestern and also the southeastern US, which is evident in the two observations. But E3SM, alongside the multimodal assemble mean, grossly overestimate the northwestern precipitation of winter precipitation of the US. And these biases, we attribute it to the inability of the model to accurately resolve a orographic process. As you know, the western part of the western half of the US is full of topography. So their inability might have resulted to this gross overestimation we observed. In the summer, one notable limitation we found is when you look at the high precipitation center over the central US, which is evident in the two observations, is lacking in the two models, both the assemble mean of the semi-6 and also the E3SM. So the model limitation in the summer is the inability to reproduce the high precipitation center over the central US. Now, when you look at the frequency of days with precipitation rate greater than 1 millimeter per day in the winter and also in the summer. So when you look at the model, you can see they tend to rain too frequently, and which is evident over western half of the US, particularly over the northwest, both in the semi-6 multimodal assemble and also the E3SM. In the summer, however, the high frequency precipitation is evident in the southeastern US. When you look at this compared to the observation, you can see a gross overestimation. Now, for the more extreme parts, 98% daily precipitation rate. So in the winter and the summer, you can see that the more extreme part is extremely weak in the two models when you compare to the observation, especially particularly in the winter over the southeastern US, and in the summer, the high heavy precipitation event in terms of the 98% over the central US is lacking in the model. So tentatively, based on this, we can see that the recently released version of the CNIP model, the semi-6, has not really alleviated the obvious biases in the previous versions. So aside from the climatological assessment of the model, we also look at the statistics, their ability to reproduce that. So we look at the percentage bias, normalized mean square error, and the pattern correlation coefficient. For all the 9 indices, which I earlier defined, so these are how the model, and these biases and the error were calculated relative to the CPC observation. So another thing we did here is that the model were arranged in order of their decreasing horizontal resolution. So to the left, you have the high resolution model, to the right, you have the lowest resolution. So based on the percentage error, you can see that the error is particularly large, positive biases in the winter compared to the summer. So you still have a fluctuating dry or wet biases in the summer, but it's not as pronounced as in the winter. Another interesting thing we found is when you look at sometimes for some indices, especially the extreme and the heavy rainfall event, for low resolution model, the error is particularly lower, even when you look at it compared to some high resolution model. And the tentative conclusion here is that simply increasing horizontal resolution of the model doesn't necessarily lead to improvement of their representation of extremes. So sometimes they have to look inward into the model physics and also explore super-parameterization option. Overall, in terms of the normalized root mean square error, which is sometimes not sensitive to especially averages, the error is mostly less than 1, except for a very heavy rainfall event, that is R20 mm, which across the two seasons consistently has the largest error. In terms of the pattern correlation, most of the indices, the model were able to capture, at least to a large extent, the extreme indices here, and you have pattern correlation greater than 0.8, except for the R20, which has the largest error, that has a pattern correlation of less than 0.7. Now, based on the insight of the evaluation result, so we proceeded further to look at the ability of this model to provide a meaningful insight in the future. So I present the projection result of seasonal precipitation extremes. So here, this is the frequency and amount distribution for the summer and also for the winter. And this is based on the assembled mean, the multimodal assembled mean. Again, the shading is the confidence interval. So when you look at the summer, the frequency distribution exhibits a decrease, especially for rates below 30 millimeter per day on the average. And there's a slight increase when you look at the rates above 30 millimeter per day. The signal for the summer is much clearer for the amount distribution, such that there is a reduction and intensification of light to medium rate and heavy precipitation rate there. Unfortunately, the projected changes in the summer is fraught with uncertainty. As you can see, the confidence level is wide. In the winter, however, there is a projected decrease in the frequency of light precipitation rate and future intensification of medium to heavy rate. The most robust signal here is the winter amount distribution, which to a high level of certainty, there's evidence of future increase, especially for rates between 10 to 100 millimeter per day. Another interesting and take-home message here is where the change in sign occur in the two seasons. In the summer, the change in sign from the decreasing light to medium to heavy rate is about 35 millimeter per day, whereby in the winter, it's about 5 millimeter per day. When you look at the temporal evolution of these projections, especially for extreme. So here, I present to you the area average, weighted average over the entire conus of summer seasonal precipitation extreme here for the summer. So again, CDD is a consecutive dry days. That is precipitation when precipitation is less than 1 millimeter per day. The RX5 is the maximum 5-day precipitation. Consecutive wet days greater than 1 millimeter per day. And the R95 P-total is the 95 percentile precipitation. So when you look at it from the present day to the end of the 21st century, there is, of course, with wide range of uncertainty, as you can see from the confidence level, there is going to be a future increase in the dry days over the entire US. Also, you're having something like a compounding extremes. So as you're having a slight increase in the dry days, we anticipate more of maximum 5-day precipitation and also extremes. Wet days intensity is going to reduce, especially towards the end of the 21st century. Based on this, we cannot be confident on the projection of the summer extremes due to this wide range of uncertainty, as I mentioned. For the winter, the projection is much more clearer, particularly for wet extreme, maximum 5-day precipitation and the precipitation greater than 95%, which shows obvious future increase reaching up to about 30%, especially at the end of the 21st century. The changes in the consecutive wet days is not obvious, and that of the dry days, there's evidence of decrease, even though the uncertainty is wide. Now, in a way to get a clearer picture, so we look at the spatial changes over the entire US. So the grid here is based on the subdivision of the National Climate Assessment. So you have the Northwest, the Southwest, North Great Plain, South Great Plain, the Midwest, the Southeast, and the Northeast. And here, I'm also presenting the area average weighted changes of all these subregions. This is the entire US. So another thing we did is the bars are the assemble mean changes. So individual model changes is overlaid. So you can see how many models agree on the projected changes in the assemble mean, and if there's a wide range of uncertainty, like half of the model agreeing or half of the model disagreeing. So as I discussed earlier, in the changes, there are two statistics which we overlaid. So where you see steeplings, that is grid points where the changes, where you compare the time slice of the future versus the historical, is statistically significant. And the hatching is the grid point where at least 70% of the model agree on the sign of change in the assemble mean. So when you look at the projected changes in the extreme, in the full paper, we look at the changes in all the 9 extremes. So for the dry extreme, which is the consecutive dry days, there is going to be a robust future changes, especially over the North Great Plain and also the Midwest. As you can see, the changes is statistically significant, and more than 70% of the model agree on the sign of change. And this is particularly evident when you look at North Great Plain, particularly Midwest. Almost all the model agree on the sign of the assemble. All but one agree over the North Great Plain. So in the Southwest here, the assemble mean is projecting decrease, but when you look at it, half of the model agree and half of the model disagree. So except for these two major sub-regions, the North Great Plain and the Midwest, where a robust projected increase in the dry days is evident in the future, the other changes over other regions is full of uncertainty. Now for the wet extremes, the summer future projections of wet extreme ranging from consecutive wet days, maximum 5-day precipitation greater than 95%, is full of a wide range of uncertainties. As you can see, grid point where there's evidence of future increase is either not significant or we don't have at least 70% of the model agreement and the changes. And this is mostly obvious when you look at the area weighted changes. So where the assemble mean is projecting a decrease in extreme in Northwest, for example, half of the model disagree to the change in the assemble and half agree on that. So except for the changes in the dry days, the wet extreme summer changes is full of high level of uncertainty, and thus the projection result is not certain. On the other hand, for the winter extremes, so particularly over the northern half of the US, there is evidence of future decrease in dry days. And this is evident, as you can see, over the Northwest, North Great Plain, Midwest, and also Northeast. You can see that most of the model agree on the sign of change in the assembly. In the southern US, however, especially particularly southern tip of the Southwest region, and also the southern part of the South Great Plain, there's evidence, and also reaching up to Mexico, evidence of future increase in dry days, and which most of the models agree to that. But when you look at the winter wet extremes, particularly maximum 5-day precipitation and the precipitation greater than 95%, all the grid point over the US is showing evidence of future increase. And this projected increase is highly robust. As you can see, most of the model, or all of the model, agree on the sign of change in the assembly. So we've evaluated the 76 model and noted their limitation, particularly their inability to reproduce the climatology, spatial climatology of precipitation both in the winter and the summer, which we observe evidence of their gross of exaggeration of winter precipitation over the northwest, their inability to capture the southwestern, the high rainfall over the central US. Also, their inability to, their, what they call it, limitation in terms of having too many frequency of precipitation. So here, we look at the potential added value of high resolution and also super-parameterizations. So in these, we ran 3 experiments, the convectional part, which was represented in the 76 model, the low resolution, average of 100 kilometers. The high resolution is about 25 kilometers, and the super-parameterization, so you have the embedded cloud resolving model at about 1 to 2 kilometers scaled, integrated into the low resolution. So I present also the result of the frequency and amount distribution from all the 3 configurations. The CPC and the HIMAG are the observation. So the low resolution is in purple, high resolution is in red, and the yellow is the super-parameterization, which people refer to as a multi-scale modeling framework. So the most obvious part is evident in the amount distribution, both in the winter and the summer. And you can see, compared to all the 2 configurations, high resolution and the super-parameterization, you can see the low resolution is doing badly, which I've earlier reported. And when you decompose these into the part that is contributed by the convection, the convective part, and the large scale part, you can see in the low resolution both the convective part and also the high resolution is contributing to these gross overestimation in the amount distribution, in both seasons. Now, especially when you look at the mean precipitation, so don't forget the low resolution, which I earlier reported, there's over-exaggeration of precipitation climatologically in the northwestern US. So we're able to improve on that via high-resolution modeling. You can see this over-exaggeration has been reduced significantly. In the summer, the high rainfall center that is lacking in the low-resolution model is able to be improved. We're able to improve on that through super-parameterization. And this is so because climatologically, the winter precipitation over the US is largely due to extratropical cyclone and large-scale circulation events. So with high resolution, we're able to improve on the representation of these large-scale events. In the summer, the main contributing factor is the mesoscale convective system, and that is, we're able to improve on that through super-parameterization because of our ability to explicitly resolve the convection in the cloud resolving model. When you look at the more extreme part, the 90th percentile, you can see there's an improvement in the intensity. When you look at the low resolution, in the high resolution, we're able to improve the intensity, which is similar to the observation. In the summer also, through parameterization, we're able to improve on the low resolution. Don't forget that the low resolution, their limitation is their inability to represent the extreme event, which we're able to improve through super-parameterization. So spatially, it is obvious that the relative added value of high resolution and super-parameterization is seasonally dependent, such that high resolution improve mostly the winter precipitation and the super-parameterization improve on the summer precipitation. So the conclusion for my talk, I hope I didn't go too fast. So the first question we asked is, how do the conventional 76 model, including the E3SM, represent extreme precipitation statistics and their projected changes? So the take-home message is that the 76 model underrepresent the intensity of the summer and exaggerate that of the winter. Particularly that of summer is evident over the central and eastern US, and in the winter is evident over the northwest and mostly the northwestern half of the US, or western half of the US. The model, both the 76 multimodal and the E3SM, generally overestimate the mean precipitation in the winter over the climatological dry northwest, and the intense summer over the rainfall center, which I've explained, is underestimated in the summer. So generally, the model exhibits too many wet precipitation days. And this is consistent to the documented limitation of the previous generations. So the relative performance of individual model, again, as we've seen, depends on the choice of the reference data sets. In our evaluation result, we can see that some models are closer to the CPC, most of them are closer to the CPC than they are closer to the dream observation. So when evaluating it, it's good to look at multi-data, multi-observation grid data set. Under global warming, and based on the RCP 585, SSP 585, there is a robust projected intensification of winter extremes, and also we found a robust future increase in dry days in the summer, particularly over the North Great Plain and the Midwest US. And as we can see, the extreme precipitation events can have different impact, particularly in winter versus summer, which is what motivated the seasonal scale analysis. So the observed intensification, or the robust intensification, which is evident in the winter, is expected to have implication on flooding, transportation, and energy use during this period. So another question which I ask is, do high resolution and super-parameterized configuration provide a more realistic representation of precipitation intensity over the US? And based on the result, we can see that improvement is seasonally dependent, such that high resolution improved the intensity of precipitation in the winter, particularly over the Northwest and the eastern years. Why super-parameterization, through its improvement of the convective process, improve the intensity of precipitation in the summer, especially over the central and eastern years. Thank you very much.
Thank you very much. Questions from folks?
Yes, please.
For the winter precipitation, you have the change in dry days. Is your work or these models capable of detailing the type of winter precipitation? So I'm left wondering, what's going to happen to winter snowfall?
So in this research, we didn't look at the snow, but the precipitation which we are looking at is a combination of both coming from the convective and the large scale, which account for almost everything. And that goes into the calculation of the extremes.
Okay, thanks for a great talk, by the way. So I'm not too familiar with what actually goes into climate models. I'm assuming there's some combination modeling the physics of the processes and then constrained by the data. In the beginning, so you made a big point about how resolution is important. And then, if I understood you correctly, at some point the resolution was increased, yet the fit was not better. That would make me panic if I so why? And
so the way it works is, so when we're simulating, so climate model, it's like you're looking at grid cells. So for the low resolution, when we say the grid cell is 100 kilometers, that means if you have a data point here, the next data point will be 100 kilometers away. Unfortunately, the processes that result in precipitation happens on the smaller scales, lower than the grid cells of the model. And thus, these processes are parameterized. Equations are used as an assumptions. So for the low resolution, it's based on parameterization, assumptions. Now, moving to the cloud resolving part, like the parameterization, then we can eliminate these assumptions and explicitly resolve the processes. Now, at high resolution, which is high enough, about 25 kilometers, to capture the large scales, extratropical cyclone, and all the dynamics influencing the winter precipitation, that was why we were able to improve on some features of the winter. In the summer, because we use super-parameterization, which has eliminated the parameterization based on the cloud resolving model, we're able to explicitly resolve convection, then we can improve on the winter. So a combination of these two approaches based on this work is able to improve the overall seasonal precipitations. So maybe in the future, with the advent of development in the model, if we can put the cloud resolving in high resolution, perhaps we'll be able to resolve the full annual precipitation.
But they're essentially almost two different models.
Yeah.
The low resolution, high resolution includes physics that low resolution doesn't.
Kind of, yeah.
Gotcha.
So
Okay.
the CRM is embedded on the low resolution for now,
Mhm.
yeah. So in the future, we're looking at how to impose the CRM, the cloud resolving model, on the high resolution. But it's computationally expensive. And, yeah.
Do you have can you compare the computational cost of the high resolution versus the cloud resolving model?
Yeah,
Are
we
those
can.
similar computationally?
So in this work, we try to force them to the same computational cost, and that has to do with adjusting the grid sets. So you can do that. Yeah.
Okay.
Yes, please.
It probably falls from Dave's question, but where are we in terms of parameterizing clouds and models? I recall like a talk a number of years ago, when someone said this is really a difficult problem, and a lot of models have trouble accounting for it. So what's kind of an update to
So there has been
cloud parameterization?
Yeah, so again, that's not my area of special expertise, but there has been significant improvement in recent time, partly because we have more observation through satellite, which has been serving as a background for improvement in this area. And the overall improvement in the cloud parameterization is also leading to the slight improvement we are seeing in the Earth system with the ability to represent precipitation. But we are not there yet.
Thank you.
Yeah.
Are there any aerosol feedbacks included in any of these CMAP6 models?
Yes, so it's a full
that's
coupled model,
incorporated
yeah. And again, that is why in recent time there's been transitioning from the global climate model to Earth system model because of more representation of Earth features. Yes.
So you use two observation data, CPC and TRMM?
For the first part, and the last part we look at IMAG. Yes.
Yeah, I noticed that even these two observations are quite different from each other. So as a modeler that I use precipitation as a forcing data, the uncertainties in the precipitation is like a pain for me. So what's your comment on what data set should we use?
So again, that's one of the conclusions of the work. The sensitivity, the performance of the model is largely dependent on the evaluating observations. So my approach is to consider as many as you can. So, and when you're reporting the results, you can say, so model is closer to so data set than the others. Yeah. Yes, thank you.
You've mentioned the sensitivity a couple of times to the models of the input data. And I think on some of the coverages, if I saw correctly, it seems like you have Canadian data. But on the observation side, you don't have the Mexico data. What kind of influence, if I saw that correctly, what kind of influence would having quality northern Mexico data do for improving your southern U.S.?
So the gridded data set we used, so what the process for the gridded data sometimes is combination of ground-based observation and satellite. And because the data sets are unevenly spaced, so the gridded approach, they use the algorithm to space them into equal grid set. So sometimes 0.5, 0.25, 0. So even regions where you have sparse observations, at least based on improvisation, you have representation. It could be like sourcing from satellite or the analysis. But this particular work and also the area averages was conducted over the US. So though you can see Mexico in some of the spatial plots, but it was not considered. Yeah. Yes.
Since we have no time,
Yes.
just interrogate you. Would the model ever, again, without knowing too much about climate models, but this is fascinating, would a climate model, given the physics that goes into it and data that you use to constrain it, ever be able to predict an event that is more extreme in some sense than anything we've seen historically?
So we are doing that, and that is why my approach, and which is also common in recent time, is we don't just use like a single model for projections. We use multi-model approach. And not only you're looking at what is the sample saying, how many of this model agrees on that. And we believe if you're using 20, 30, 40 model, about 70 or 80% of them are saying this is the direction. To a larger degree of certainty, we can say that is the expectations. And don't forget, this is projection. So generally in the climate science, the accuracy increases when you're getting to the event. So in the weather scale. So in the future, things might change based on the improvements we are seeing in terms of political awareness to climate change, reduction of emissions, and all of that. But currently, at the current state, this is the expectations. Yes.
So in your projected work, so in summertime, your CMIP6 data projected that there will be less of consecutive dry days in the western U.S. Because my research focus on western U.S. so I care more about that. Does that suggest?
So the only projection for the dry days that is robust is the North Great Plain and the Midwest.
Okay.
So I decided not to emphasize on any changes that is not robust because it's full of uncertainty.
Okay.
So the only expectation based on these will be over the North Great Plain and the Midwest, where we should expect dryness.
Okay.
Yeah. And when you look at also the winter extremes, the wet extremes in the summer, even though most of the grid point is blue, which is positive, you can see the grid point that statistically significant or have at least 70% of the model agreeing on it is limited. And that's particularly more obvious on the area with exchanges, where you see the sample saying positive and half of the model say no and half of them say yes. So when you have wide range of uncertainty, it's better not to count on that. Yeah. And that's different from that of the winter, where you see that for the wet extreme, most of the model agree on the sign of change. And back to your question, when we see these, then we can be confident that we should expect something like that in the future, yeah. All things being equal. Yes?
I have a question about the winter dynamical changes that you're predicting, and particularly the increase in confidence that you have in the higher resolution simulations in the winter. And I know you mentioned mesoscale convective complexes and tropical cyclones. And I'm just wondering, have you done the systematic analysis to figure out precisely the dynamics that are changing, like storm track location, pressure centers?
Yeah, thank you. So we have a paper now under review, which is basically on the mechanism modulating the observed changes. And that's, which is essentially focused on the winter, where we have the robust changes in the extremes. So we look at the storm tracks, diagnosing the moisture budgets, to look at which of the mechanism is responsible for the changes in the terms. I can share that with you.
Okay. Yeah. Do you know, just anecdotally, for the Pacific Northwest, let's say, do you know what about the high resolution dynamics is changing at the higher resolution simulation that is changing the Pacific Northwest precision?
No, I didn't get the question, sir.
So in the Pacific Northwest, at the higher resolution model does a better job of capturing the precipitation. Do you know what dynamically is changing there? Is it?
No, I don't.
You know.
Yes, sir.
Defining your significance threshold in terms of the fraction of models which agree in predicting the same sign of change, seems you're implicitly assuming some significant degree of independence between the models. But are there some subset of the models that are so similar that they always predict the same sign? And does that somehow affect your estimate of the significance?
Yeah, thank you for that. That is a very interesting question. So in terms of model dependent, the only conclusion will be if you have a GCM coming from the same institution. So for example, if I go to the list of the model, here. So for example, if you look at this model, it's from the same institution. One is a medium resolution and one is the low resolution. But aside from that, we can only base our result on the statistics, assuming that the model are not interrelated. So the selection is based on the wide range of institutions that contribute to the synthesis project, rather than looking at multimodal in a particular institution, which can be interrelated. Yeah.
Any other questions? All right, thank you.